Namaste everyone. Welcome to second PUC physics class. We are discussing about semiconductors. Now, today we will go deep into the doping, that is incorporating some other impurity materials into N-type, P-type semiconductors. Namaste. Hope you are doing well. So, we will move on. Yesterday, in the previous class, we have seen about how to produce a N-type semiconductor. We have two types of semiconductors, intrinsic and extrinsic. What do you mean by intrinsic and extrinsic? Naturally available semiconductors are called intrinsic semiconductors. They are not doped. They have equal number of holes and electrons at room temperature, because at 0 Kelvin, no electrons and holes. All the electrons and holes are intact. There is no electron escaping from any type of bond work. It is always engaged in bond work. So no electron is free, no hole is produced. Charge carrier 0. It is a perfect insulator at 0 Kelvin. But as the temperature increases, when you bring it to room temperature, that heat energy is far more than enough, and electrons can absorb the energy and they can go to the conduction band. That is one theory. And another way, if you want to explain, electrons, these atoms can vibrate and some bonds may be broken and electrons become free. So many free electrons are created and equal number of holes are created. So intrinsic type of semiconductor is a type of semiconductor which contains equal number of electrons and holes. Both the charge carriers are equal in number, but both will flow and produce current. And remember that the flow of electrons and holes do not produce opposite current. That produces the same direction current. How? If electrons move in this direction, current is like this. Then definitely holes will be moving like this. So current gets added up, because current is the flow of charges. Electrons, because if you see, if you have an electric field, electrons and holes, even though they move in opposite direction, field is same. So that current is the total current in a semiconductor is the total is the current due to the flow of electrons as well as the current due to the flow of holes. That gets added up. So current in a semiconductor, I, is equal to current due to electrons and current due to holes. It gets added up even though they move in the opposite direction. Now, so intrinsic type of semiconductor is a type of semiconductor where a number of holes and electrons are equal. It is not doped with impurities. All the material, all the atoms will be the semiconductor atoms only, and they are tetravalent. So if you want to have an N-type semiconductor, what you have to do? You have to take an intrinsic semiconductor. Any intrinsic semiconductor doped with some impurities is called extrinsic semiconductor, where the number of electrons and holes are not equal. Either holes may be more in number, or electrons may be more in number, depending on what you have doped. That depends on the type of doping. Now, if you dope an intrinsic semiconductor with pentavalent impurity, like phosphorus, antimony, bismuth, which have 5 valence electrons. In addition to that, there are electrons in the lower energy band, but they are not free. They are very close to the nucleus, so it is not easy to remove them, and they can't take part in the production of current. They are bound electrons. So in addition to valence electrons, there are other electrons also. But even valence electrons can't take part in bonding. Take part in the current production, because their electrons, even though they are loosely bound to the nucleus, they take part in bonds, forming the bond between the neighboring atoms. They are shared electrons which are shared between the neighboring atoms. So if you take a silicon, we have drawn this right yesterday, Rangoli, silicon, yeah, it requires certain time and patience. Silicon, yes. This is the way in which we show the bond, and this is the way in which we show the bond, right? You know how if you want to lift your friend from a pit, he has fallen to a pit, I want to lift, you have to hold his hands like this, right? Like this. You should lock him here and he should lock you here, so you can pull it. So 2 locks make it very tight. That's how we show it here. So the bonds are intact like this. This is only a model. So like this. These bonds will have some silicon atoms further, which is not shown in the diagram. So like this, yes. Right. Now, there are silicon atoms, but we are concentrating on this now, silicon atom. This silicon atom, in order to make its bond very strong with the neighboring atom, it tries to donate one free electron. So one electron, that valence electron in the outermost shell. So this electron 1 is donated by silicon, donated. Fortunately, silicon has 4 valence electrons, and these 4 valence electrons are shared between 4 neighbors, because there are exact number of neighbors. So if you have 4 people in this house, if there are 4 functions going on in the neighborhood, you can send each one to the function, and so that they don't get disappointed. So what about this silicon? This silicon also donates one valence electron to this, and this, like this. And okay, this silicon donates its valence electrons, so like this, so it continues. So every silicon atom donates its one valence electron to the neighboring atom, so that the bond gets very tight, and the silicon is a strong material now. So like this, like this. Okay, somehow you have to adjust it, right? But when the temperature increases, atoms will vibrate, and one bond will be broken, one electron becomes free. Suppose this electron becomes free electron. That free electron has created a broken bond, right? And that bond may be completed by the motion of any electron somewhere else. So an electron from here may definitely come here and fill this bond. But this electron, when it comes, it was a bound electron earlier, and it is a bound electron now. So its motion is not called free electron motion. But this vacancy has been shifted here. So we call that as a motion of positive charge, the opposite to the motion of electron. That is called motion of hole. So absence of electron, which carries a positive charge. That means, what do you mean by carrying positive charge? It says that I need an electron to become a neutral. That's the meaning, right? If a positive charge is found, if the hole is given a positive charge, that is because it needs an electron. So as to become neutral. So holes are positively charged. So motion of holes are possible. When bound electrons go and fill the different holes, the position of holes gets transferred. So in an intrinsic semiconductor, if one electron becomes free, then definitely one hole is created. If 10 electrons become free because of the breakage of 10 covalent bonds, then 10 free holes are created. And remember, all these holes are in the valence band, because electrons, when they absorb energy and go to the conduction band, free electrons are found in the conduction band, but holes are found in the valence band. So, so there are plenty of electrons and holes. But this method will not be useful always to increase the number of electrons and holes in a semiconductor and make it a very good conductor. That is not possible. You have to go for doping. Doping is a process of adding impurities to the pure semiconductor. Once the impurities are added, then it is called extrinsic semiconductor, and the type of impurity taken must be such that you can't add any impurity to this. The foreign atom which has been added to the silicon or germanium, any pure semiconductor, it shouldn't disturb the crystal lattice. Crystal lattice means all the types of bond between the neighboring atoms, and the crystal structure, it shouldn't be altered. So such an atom you have to choose, and the size of the dopant atom must be exactly equal to the size of the silicon atom, so that it fits here, right? It should exactly fit to this place. So such an atom you have to take. Of course, their energy levels must also be the same. Okay, you can put it here. Now suppose you dope pentavalent phosphorus. What do you mean by pentavalent phosphorus? Phosphorus has many electrons, but there are 5 valence electrons. In the outermost shell we have 5 valence electrons, and these 5 valence electrons can have 5 bonds with the neighboring phosphorus atoms. But when they come to silicon, 1 electron becomes free, because 5 are not needed here. So when one silicon atom is replaced by a phosphorus atom, phosphorus has got 5 valence electrons, and among them the needed one are only 4, so 1 electron becomes free. Remember, this is not an extra electron, because when you bring phosphorus atom before doping it to the silicon, when you have the phosphorus atom, you ask the phosphorus atom, phosphorus, how are you? Sir, I am free, I am fine. So how many electrons you have got? You have many electrons, sir. And how many are there in the outermost energy level? Sir, there are 5. Why did you keep 5 electrons in the outermost energy level? Sir, I have 5 neighbors. I want to have a good relationship with the 5 neighbors. So I want to have 5 electrons in the outermost shell, so that they are always communicating with the neighboring atoms, so that my relationship with the neighbors is very good. So it is fulfilled. But when the same phosphorus comes to silicon valley or silicon atom or silicon crystal, when it replaces one silicon and places that, aluminium looks into the neighbors, and there are only 4 neighbors. 4 valence electrons are enough to form the bond. 1 is left free. But in the original aluminium atom, there were 5 valence electrons, there were some other electrons revolving around the nucleus, totally some electrons, and exact number of positive charges inside the nucleus. It was neutral. 5 valence electrons, some other electrons, and equal amount of positive charges inside the nucleus. Totally it is neutral. When that atom is brought here and kept, phosphorus is neutral, already silicon is neutral. We are talking about only these valence electrons, that's all. That doesn't mean that only valence electrons are present in an atom. There are some other electrons also. Totally it is neutral. That means when phosphorus is brought here and kept here, again the extrinsic semiconductor, what you call impure semiconductor, it is neutral, because this is not an extra electron added. It is also one of the electron of phosphorus which makes it neutral. Got it now? It is also one of the electron. But now it has become free, that's all. There are equal number of positive charges inside the nucleus of phosphorus to make it neutral. So this electron now can move from here to here, because it has no job at all. Unemployment for this electron. It has nothing to do now. There is no bond remaining to complete. So it can move from one atom to atom. But one thing you have to remember, phosphorus has become positively charged. But still this electron will be in the material, so the whole material is neutral. So addition of phosphorus atoms creates more and more free electrons. Addition of one phosphorus atom creates one free electron, and many phosphorus atom creates many free electrons. That is why phosphorus is called donor impurity, because it donates one free electron. Donor impurity. Remember, it doesn't create one free electron. That electron was also an electron, a part of the phosphorus atom, but it has become free now, that's all. It is not an extra electron created. So donor impurity, that is pentavalent impurity. Pentavalent atoms like phosphorus, bismuth, antimony, they are called donor impurities because they donate one free electron. Okay, so addition of donor impurity creates more and more electrons, and that type of extrinsic semiconductor is called N-type semiconductor, because we have negative charge carriers more. This is what happens at room temperature, and even we can find many free electrons. So now at room temperature, again I was explaining yesterday, at room temperature there may be 100 doped phosphorus atoms. Say simple number I will take, 100 doped phosphorus atoms inside the silicon. Then how many holes are produced? How many electrons are produced? 100 holes, 100 electrons, no holes. Because doping of pentavalent doesn't produce holes. Okay, now because of thermal, so this is because of doping, say. Because of doping we have 0 holes, 100 electrons. Because of thermal energy, thermal excitation, say there are how many holes? 10 holes and 10 electrons are produced. Because of supply of heat energy, electrons have absorbed it and went to the conduction band, means same number of holes are created in the valence band. So 10 and 10, what is the total number? Now whatever be the electrons and holes, totally there are 110 electrons, 10 holes. So they are called majority carriers. So there may be few holes also in a N-type semiconductor. But remember, these holes are not because of doping, they are because of thermal energy. but their number is very, very less because we dope it with many, many free electrons. So electrons are majority carriers in N-type semiconductor, holes are minority carriers. Okay, these differences are very important and very easy to remember. No, nothing much memory is needed, ideas are needed. Okay, now we will go to P-type semiconductor. What is a P-type semiconductor? A trivalent impurity is added instead of silicon. Suppose this is silicon at okay, that is 0 Kelvin, right? Remember, at 0 Kelvin, what happens? All the bonds are intact, no electron is free, silicon is a perfect insulator. Bring it to room temperature. So holes, electrons at room temperature. That is thermal excitation, right? Thermal energy. Say 10 holes and 10 electrons are created. Now bring some 100 boron atoms. Not in 100, we dope it in a large number. 100 boron atoms. What is a boron atom? An atom which has got 3 valence electrons. At the outermost energy level, they have 3 valence electrons. That is the valence band. So 3 valence electrons can form bond with the 3 neighboring atoms. What about one neighboring atom? One neighboring atom says, silicon atom says, don't I have any electrons shared from you to me? I don't want to share any electron with you because I don't have so many electrons. I have shared already the 3 electrons available here. What about the 4th one? Left vacant. So a hole is created. Addition of one boron atom to a pure semiconductor doesn't satisfy all the bonds with the neighboring atoms, so one hole is created. And this hole doesn't have its pair electron because this hole is created because of boron atom. Remember, when boron atom is brought, boron was having 3 valence electrons, some other electrons inside, and this total number of electrons is equal to number of protons inside the nucleus. Boron was neutral. When boron atom was kept here, it was neutral, and that boron atom, when it came here, it couldn't satisfy one bond, so one hole is created. Still it is neutral, the whole material is neutral. So this type of semiconductor is called P-type semiconductor, and this is also extrinsic. Both N-type and P-type are extrinsic semiconductor. So how do you get a P-type semiconductor? When a pure silicon or germanium semiconductor, which is tetravalent, needs 4 valence electrons, is doped with the trivalent impurities like boron, indium, gallium, etc. The 3 valence electrons can form 3 covalent bonds with the neighboring atoms, but the 4th bond is left vacant, and that creates a hole. And if you dope it with very many boron atoms, many holes are created. And such a type of extrinsic material, which is not pure, containing external impurities, is called P-type semiconductor. And now, since each boron atom creates one hole, to complete all the bonds, it needs 1 electron. So boron or trivalent impurity is called acceptor impurity. Trivalent impurity is called acceptor impurity because it wants to accept one electron. Pentavalent impurity is called donor impurity because it can donate 1 electron free. This wants 1 electron, this needs 1 electron to make the bond complete. So it is called acceptor impurity. So addition of acceptor impurity creates more and more holes, and now you get P-type semiconductor. P-type semiconductor, because positive types of charge carriers are more, that's all. It is not positively charged. Again, P-type semiconductor is also neutral. Okay, now, I will add 100 boron atoms. 100 boron atoms. When they are added, you get 100 holes and 0 electrons. 110 holes, only 10 electrons. So who are majority? Majority charge carriers are holes. This is how we get a P-type semiconductor. So you may get a difference. What are the differences between N-type semiconductor and P-type semiconductor? You can write many differences. Both are extrinsic. In N-type semiconductor, electrons are more in number, majority carriers. Holes are minority carriers. In P-type semiconductor, holes are majority carriers, electrons are minority carriers. Of course, you can split it into two parts, two differences. And what else? N-type semiconductor is always obtained by doping a pure semiconductor with pentavalent impurity, whereas P-type semiconductor, to get P-type semiconductor, we have to dope trivalent impurity to a pure semiconductor. So like this way. And both will have more conductivity. The conductivity of a semiconductor is increased now. How? By doping these impurity atoms and by creating more and more charge carriers, either maybe holes or electrons. So as you dope a material with P-type or N-type, what happens to the conductivity? Conductivity increases. So conductivity of a semiconductor increases, its resistivity decreases, opposition to the flow of charges decreases as we dope it with more and more pentavalent and trivalent impurities. Whether it is a P-type or N-type, whatever it is, because holes are also the charge carriers, electrons are also charge carriers. So why you need to worry? We need only the charge carriers. So whether you dope it with the pentavalent or trivalent, resistance decreases, resistivity decreases, conductivity increases. So that's how we change the conductivity and resistivity. Suppose you want the conductivity to be very, very high and that is resistivity to be very low. It should oppose a little bit. It should conduct more. Dope it heavily. If you want the resistance not very low, some fair good resistance, dope it not with too much of boron or pentavalent atoms. Dope it fairly, then it will have some resistance. So these are the two types of semiconductors: impure semiconductors, extrinsic semiconductors. P-type and N-type both are neutral. Okay, so that's how we get them. And this type of doping is not such an easy job. It is done in the laboratories. You can't do it in open ground or so. It's a macroscopic experiment. You can't do it as easily as you think here. But still it is possible. So that's why nowadays we have a high application for semiconductors. We use it in technology in a large scale. Silicon chips, ICs, microprocessors, all made up of silicon and germanium semiconductors. They have high application. The reason is you can control the charge carriers. That is what you call semiconductors, semiconductor electronics, right? It's a separate branch of electrons, semiconductor electronics, where we have the control motion of charges by doping it into the different level. Now, what is the use, sir? Once you get P-type, N-type and semiconductors, by changing their bonding and type and producing more and more free electrons or holes, what is the use? You can construct different types of devices. One such device is called p-n junction or a diode. P-n junction or a diode. Di means two, right? Diode. In the olden days, I was saying, if possible, I will bring it and show it to you. How in old radios, you have seen some old radios in exhibitions, it was very big like this. It was very large, and if you open it, you will have valves, vacuum tubes. They were doing the job of amplification and oscillation and reception of signals, and all these were done by those valves. They were very big in size. Nowadays, we have a small chip which works very similar to crores and crores of valves, which performs the job of crores and crores of valves, is done in a small chip. It is miniaturized. Power consumption has been reduced. So we have gone to a tremendous revolution after the invention of these semiconductors. Now one such step that is a milestone in the invention of semiconductor devices was diode. Di means two. Diode means two ends, two terminals, two regions. That is diode. Now, how do you construct a diode? Take a semiconductor. We can already call it as masking. Suppose you have a semiconductor, say silicon, pure silicon semiconductor. It is not doped with impurity. Mask one side. What do you mean by masking? We don't dope it because it is not affected while we are doing something here in the other half. If you are doping this with trivalent impurity, this shouldn't be get affected. That is what we call masking. So mask it on one side, dope it with the trivalent impurities. And when you dope one side of the semiconductor with the trivalent impurities, what happens? More holes will be created. So shall I show those holes as like this? That doesn't mean that I am showing positive charges. Remember that I am not showing that this is positively charged. I am showing what are the free charge carriers. I am not showing that I have some extra positive charges compared to the negative charges. No, 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 no. There are equal number of positive charges as well as negative charges. But who are free? When you compare free numbers, holes are more. As if, for example, in a school, suppose there are 100 boys and 100 girls. Imagine 100 girls are sitting in the classroom and listening to the teacher, right? And out of boys, only 90 are sitting in the classroom and remaining 10 are wandering in the corridor. If somebody observes the college, then they say that 10 boys are roaming around and they are free boys. Does it mean that we have more 10 boys? No. Among 100 boys and 100 girls, 10 boys are free. 90 boys are in the rooms, classroom, sitting and listening to the class. So, what are these positive, 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 positive? They are not extra positive charges. There are some other positive charges also. There are some other negative charges also. Totally it is neutral. Once again I say, I didn't show that this end is positively charged. There are more number of holes. I am mentioning free charge carriers. So if I go on mentioning a college with those number of students who are not listening or not attending the class, if I identify colleges A, B, C, D like this, those who are not listening by a number of students who don't listen to the class or who don't attend the class, like this: A, say 10 boys, B, 20 boys, C, 30 girls, D, 50 girls, like this. What does it mean? Whether college A has got more 10 boys and last college D has got more 50 girls? No, not like that. Among the neutral or total equal number of boys and girls, how many are not listening to the class? That is the meaning. Similarly, among the all positive and negative charges, who are free here? Positive charges are free. What about here on the other side? Okay, that is over. One side is masked. Remove the mask. Mask it this side. This doped with the pentavalent impurity. You know, the pentavalent impurity like arsenic or phosphorus donates one free electron, and that electron is not an extra electron. It contains a positive charge inside the nucleus of phosphorus. It is neutral. Totally it is neutral. So if you ask me what are the charge carriers in N-type semiconductor, they are the electrons. So electrons more in number, charge carriers, majority charge carriers. Sir, what about this side? Will it contain some electrons? Yes, there are some. Because I have, minority carriers are electrons. Sir, how come electrons here in the P side? P-type semiconductor. This is P-type. This is doped with the trivalent and this is doped with the pentavalent. So we have P-type and N-type. How come electrons here? Very few. Because this material may be now in room temperature. When it is in room temperature, some electrons get excited to the conduction band, so that produces equal number of holes in the valence band, equal number of electrons and holes. Out of all these plus 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 marked free holes, all may not be because of doping. Some may be thermal excited, right? So you ask one by one hole, whether you have been here from because of doping atom, whether you are from boron atom. Some holes will say, yes, I am from boron atom. I am from boron atom. Some holes will say, no, 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 I am not at all related to boron atom. I have been created by a thermal excitation of an electron. So those thermally excited electrons will be here. Definitely out of these three electrons will say that there are some 3 holes somewhere here which are because of thermal excitation. As I gave that number 110. Out of 110 electrons, 100 are from doped phosphorus atom, pentavalent. Whereas 10 are thermally excited. So there should be 10 holes also there. So there may be few electrons and same number of holes in between these holes which are from thermal excitation. So similarly, can I show some positive charges here? You ask them, from where did you come in N side? We have been doping this right side with the pentavalent impurity. How come holes? Holes say, you ask all the electrons. Out of all the electrons, they are not from N-type. or they are not from pentavalent extra electron. Some of them are from thermal excitation. So we have our friends 3 electrons between those all electrons, they say. So there may be minority carriers. So I can show them. And now mask one side and dope it with pentavalent impurity. Mask another side, dope it with p-type material. That is convert it into p-type semiconductor. That means dope it with trivalent impurity. Remove the mask. Now the diode construction starts. At the junction, this is called p-n junction. This junction is called p-n junction. Now at the junction, what happens? Very interesting now. Always anything wants to be neutral, and we find that there is an equilibrium, there is a tendency to reach equilibrium in any case in our nature. This side rich with free electrons, this side rich with holes. So what happens? Very scarcity of holes, scarcity of electrons. So n side contains plenty of free electrons and p side contains plenty of holes, but less electrons. So the concentration of electrons on the n side is more, concentration of electrons on the p side is less. Concentration of holes on the p side is more, concentration of holes on the n side is less. So there is a diffusion from higher concentration to lower concentration. Electrons from n side will start moving towards the p side, and for this motion no external battery or no external energy is required, because it is just a motion because of higher concentration and lower concentration, and this is called diffusion. So diffusion of electrons from n side to p side and diffusion of holes from p side to n side starts. Where does it start? Mainly at the junction. Here. This starts at the junction, because here it is easy to flow, right? Imagine that there are 2 states, Karnataka and Tamil Nadu. Say simple and very bad example I am giving. And suppose in Karnataka there are more engineers. Everyone, and all the Karnataka people are having a passion of becoming engineer. It is having plenty of engineers, crores and crores of engineers. Imagine that all Tamil Nadu people have a craze towards medical. All are doctors. Tamil Nadu is rich with doctors. Karnataka is rich with engineers. Now, if all people, most of 99% of the people in Tamil Nadu are doctors, whom they will treat, right? They don't have patience. So what they will do? One doctor in Tamil Nadu will think of, no doctors in Karnataka. If I go there, I will get more number of patients, I can earn money and I can see my life there. Similarly, an engineer on the Karnataka side will think of, the engineers on the Tamil Nadu are very less. If I go there, I will get plenty of work. So there will be a migration. That is called diffusion. So migration of majority carriers from one side to the other side. Here also the majority carriers from one side to the other side. So electrons from one side, n side move to the p side, holes from p side move to the n side. And this migration starts first here at the border of the 2 states. They quickly go here and there because it is very easy to transfer. So one electron moves from here to here, say, because there are more electrons. And remember, that is the 5th electron of phosphorus atom. And when that electron moves from here to here, what do you mean by this one? It has been doped with boron atom. Boron atom will be very sad because I couldn't satisfy all the neighbors. I was having only 3 valence electrons, but 4 neighbors were waiting. So one electron comes here and fills that bond which was vacant because of boron atom. So what happens now? One electron from n side can come to the p side and can fill that bond. But once that electron fills that bond, now it is not free. It is bound now. So an electron from n side, which is an extra electron for forming the bond because it was doped with pentavalent impurity, can move to the p side where the concentration of electrons were less and can complete the scarcity of bond which was created by trivalent impurity doping here. So that electron completes the bond, and now it is an immobile charge carrier now. Earlier it was free, it was ready to carry current. Now it is not free. Now it is bound. So that electron is now bound. So shall I show it like this? Minus, this is the migrated electron from n side to p side. Now you compare the 2 materials. Earlier, N-type of semiconductor was neutral, P-type semiconductor was also neutral. When the junction is formed, of course totally was neutral. When the junction is formed, an electron came from N-type side to P side. Now you ask a phosphorus atom here. Phosphorus. You had 5 valence electrons. 4 you gave it to the neighboring atoms for forming the bond. 1 was free. Where is it now? Phosphorus says, oh, it has gone to the other side. Now this is a phosphorus ion. Am I right? It has lost 1 electron to the other side, and now it is a phosphorus ion. Did you get this? Why it is so? Because that electron, even though was not forming any bond, it was there within this material. That 5th electron, even though it was not engaging in any bond, it was there in this material N-type. That is what we were saying. N-type semiconductor was neutral. Even though 5 valence electrons of phosphorus were not able to engage in all the bond, only 4 were engaging in the bond. 5th one was free, but it was there. It was neutral. Now it has come to P-type. It has lost 1 electron. Now you ask that phosphorus whether the members in your family are proper. It says, it searches, it counts all the members. 1 is missing. Some area has gone wrong. Now I have lost 1 electron. I am a positive ion. Because losing an electron makes 1 proton excess in the nucleus. So positively charged. But that electron has come here. Now it is no longer a free electron because it has completed 1 bond. That bond is intact around boron. Now ask boron. Do you have the same number of members in your family? Boron starts counting. I have an excess electron. Last time I had no electron. Now it looks into the neighbors. It says, oh, all the bonds are completed. Some electron has come. It has become negatively charged ion. Boron has become negatively charged ion because it has got 1 excess electron. Phosphorus has lost that electron. So this exchange continues. 1 electron has come. Second electron, because there are plenty of bonds to be filled in the P side, plenty of electrons in the N side with the jobless. So more job here, no job. So another electron comes, becomes immobile, and another electron comes. I will show it with the round circle. This electron has come from some phosphorus like this, like this, like this. Hope you have understood. This migration continues, and this migration first happens in at the junction. So now if you look into the junction at the Tamil Nadu-Karnataka border, there are plenty of doctors who have migrated from Tamil Nadu to Karnataka, and plenty of engineers migrated from Karnataka to Tamil Nadu. They are rushed in border. But now the question is, will all the electrons from here come here and fill all the bonds? And this gets completely positively charged, and this gets completely negatively charged. And one thing is, totally again it is neutral. No electron has gone out of the system, and no electron has come into the system. Only comparative from this side and this side. If you compare it from this side and this side, this is positively charged, this is negatively charged. That's all. But total it is neutral again, total as a whole. Now, will it continue and all the electrons will come here and complete the bond? Will all the engineers of Karnataka move to Tamil Nadu? All the doctors of Tamil Nadu move here? Never, because if it happens so, condition is same. All the doctors in Karnataka jobless because no patients, and everybody we should test the other one, the difficult task, and all the engineers in Tamil Nadu migrated and no doctors. So that won't be the situation. Equilibrium will be reached. Why? Because when first electron comes and fits here, completes 1 bond, that boron atom has become negatively charged because it has got 1 extra electron from the other side. When the second electron comes here, that boron atom, which is a negative ion, opposes the arrival of the next electron, because you know negative charges repel, like charges repel. When the very next electron, okay, so let us assume that there is a high pressure here, because there is a higher concentration of negative charges here, more free electrons, so they come here 1 by 1. Since there is a more concentration here, some electrons may come here and fill the bond. This gets negatively charged. As it gets negatively charged more and more, the further electrons will find it difficult to move, because already arrived electrons will oppose the arrival of the next electrons. When the second electron comes with difficulty, even though this opposes, it fills a boron atom. That boron atom gets negatively charged. Now there are two electrons which will oppose the arrival of the third electron. You ask the third electron, did you move easily to the p side? No sir, I found it very difficult, because already moved two electrons have combined with boron atom, and that has become a negative ion. Now these two ions are opposing my arrival, sir. With difficulty I went there, sir. Third electron has come. Fourth one will find it still more difficult. Fifth one, utter difficult. So in this way, one by one electron, as it moves from n side to p side, it finds it difficult and difficult to move, because the negative charge developed in the p side, see, this is positive, means p-type means holes are majority carriers, but electrons, as they move here, this gets negatively charged. The negative charge developed in the p side opposes the arrival of the next electrons, right? As the engineers from Karnataka move to Tamil Nadu, they will start making their own group, and they oppose the arrival of the next coming engineers, because if the number of engineers increase in Tamil Nadu, they won't earn money as much as they were doing earlier. Even the doctors here, doctors who have migrated from Tamil Nadu to Karnataka, as their number increase, what happens is they will oppose the arrival of the next coming doctors, because their earning will decrease. So there will be groupism. So here, this positive charge, the arrival of the negative charges to this side decreases, because already arrived negative charges will oppose. So the migration of electrons and holes stops at a moment, and a layer of negative and positive ions are developed at the junction, and this region is called depletion region, a region where immobile charge carriers are present. This electron, when it comes here and completes the bond, it is no longer a free charge carrier. And as this a hole is created here, or a positive ion is created, that is phosphorus or pentavalent, it is no longer a free charge carrier now. So a layer of positive and negative charges are created at the junction, and that is called depletion layer or depletion region. Depleted means it is having some absence of free charge, absence of. It is we can't find something there. That is called depletion. Depletion means not found at all. What is not found in this region? Charge carriers. Do you have charge carriers here? Yes. Electrons. Do you have charge carriers here? Yes. Holes. What about here? Even if you have written plus and minus, it is depleted off. It is absent. You can find the absence of free charge carriers. They are all immobile ions. They can't move. They are not free. So a layer of positive charges and negative charges are created. You know that if you have a positive charge on one side, like in a battery, negative charges on either side, another side, you have a positive and negative charges developed. It acts like a battery, and this battery doesn't cooperate, or it avoids the further migration of electrons from here or holes to here. Even the holes can move. You know what do you mean by motion of hole? When electron completes a bond, we say that the vacancy is shifted to the other side. That is the motion of hole. So electrons and holes can't cross the junction, and diffusion of electrons and holes stops at a moment, because the p side gets negatively charged, n side gets positively charged. As the electrons and holes migrate, at one stage this depletion region will be so strong that it will develop a potential. What do you mean by potential? A negatively charged side and positively charged side will act like a battery, and that battery will avoid. Suppose another electron wants to come here, it has to overcome the negative, the repulsive force of all these negative charges. Suppose a hole wants to go here, it has to overcome the opposition from all these positive ions. It is not possible, migration stops. And initially, because of the migration of these electrons and holes, what the current we got is called diffusion current. We get a current because of the migration, and it stops after a certain time. Now if I ask you a question, diffusion current is due to what? Whether it is due to minority carriers, whether it is due to majority carriers. You answer me. So diffusion current is mainly due to minority carriers, majority carriers, none of these, whatever it is. Another question, the depletion region created at the junction stops the migration of, again same options, minority carriers, majority carriers, or none of these, something like that. You think it of course I am going to continue this because it's a very interesting one. You get one more type of current called drift current further, and then PN junction diode and all, and so we will study it in the next class. Thanks for watching my class. Hope you will read the notes also because it contains the explanation. You can write it in the exam. So thanks for watching my class. We will meet in the next class with a few more things, ideas and all. And till then, take care of your health. Read well. Thank you.